Okay, today we're going to learn about the basic concepts of probability. All right, there's a lot of stuff that we're going to learn today. I highly encourage you to take notes. Stop this video when you need to and follow along. So we're going into probability now, so it's very important that you understand the definitions of words and how they're used. All right, so our learning targets today are: I will know how to identify the sample space of a probability experiment and how to identify simple events. I will know how to use the fundamental counting principle to find the number of ways two or more events can occur. I will know how to distinguish among classical probability, empirical probability, and subjective probability. I will know how to find the probability of the complement of an event, and I will know how to use a tree diagram and the fundamental counting principle to find probabilities. I know that's a lot, but we're going to go through it, and this video will be available for you to review every time you need to, and to use it to finish the 3.1 classwork. A probability experiment. It's an action or a trial through which specific results, counts, measurements, responses are obtained. Like, if you're trying to get heads because you want to win the kickoff of a football game, you flip a coin. There are two results. The experiment is flipping the coin. The two results are heads or tails. The one that you want is the one you choose when the ref flips the coin. Outcome. It's the result of a single trial in a probability experiment. Sample space. It's the set of all possible outcomes of a probability experiment. Flipping a coin, rolling a die, picking a card out of a deck of 52. All right, an event, it consists of one or more outcomes, and it's a subset of the sample space. So rolling a die, you might want to get an even number, so it'd be 2, 4, or 6. Those are three possible outcomes, and is a subset of all the possible outcomes of rolling a die. All right, here's some probability experiments. Rolling a die. You want the outcome of a 3. The sample space when you roll a die is 1, 2, 3, 4, 5, or 6. An event, die is even. It'll be 2, 4, 6, like we mentioned before. Die is odd, 1, 3, 5. Identifying the sample space. The probability experiment consists of tossing a coin and then rolling a 6-sided die. Let's describe the sample space. So you have, with a coin, you have heads or tail, two possible outcomes. With each of those outcomes, you have 6 possible outcomes of the die. 1, 2, 3, 4, 5, 6. So we're going to introduce what this thing is, a tree diagram. What you do is you split up the possible outcomes of the coin into heads or tail, and then each heads and tail get 6 possible outcomes of the die, and it looks like the branches of a tree. Okay, so you have heads, and then you could have 1, 2, 3, 4, 5, 6, or you could get tails, and you could still get 1, 2, 3, 4, 5, 6, and you add up all the possible outcomes, and you obtain the sample space. So there's a total of 12 possible outcomes. Simple event. An event that consists of a single outcome, something very specific. We tossing heads and rolling a 3. So we want heads and a 3. That's very specific. It's a single data set. That's a simple event. An event that consists of more than one outcome is not a simple event. They don't have a specific name for it. It's just not a simple event. So if we want to do a heads and get an even coin die roll, then we would have a subset. We'd have heads 2, heads 4, and heads 6. This is not a simple event because you're ending up with more than one outcome. Identifying simple events. All right, we're going to determine whether the event is simple or is not simple. You roll a single die. Event B is rolling at least a 4. All right, so at least a 4. You got to understand what that means. So we have 1, 2, 3, 4, 5, 6. At least means 4 or greater. So our subset would be a 4 would satisfy the event, a 5 would satisfy the event, and 6. Because this is not a single specific outcome, it is a subset, makes it not simple. Fundamental counting principle. If one event can occur m ways and a second event can occur n ways, the number of ways the two events can occur in sequence, m then n, would be the product of m ways and n ways. The product means multiply. Can be expressed by any number of events occurring in sequence. All right, here's an example. You're purchasing a new car. The possible manufacturers, car sizes, and colors are listed. You're looking at a Ford, a GM, or a Honda. You're considering the car size of a compact or midsize. And the possible colors are white, red, black, and green. So 3 manufacturers, 2 car sizes, and 4 colors. We could do a tree, 3, and then 2, and then 4 off of each one and count them all off. But pretty soon, these trees diagrams will get too cumbersome, too big. So we use the fundamental counting principle. So we take 3 times 2 times 4. 24 ways. So when you want to know the sample size of multiple events, you multiply how many different ways something can occur together to get your total sample size. And notice if they do the tree, it's starting to get very cumbersome and very big. If we add another layer to this, it would take up way too much paper, and the probability of getting the wrong answer becomes greater. Classical probability. This is an important definition. This is the theoretical. This is done in a lab away from real life. Each outcome in a sample space is equally likely. It's probability of E, which is the event E, the number of outcomes in event E, divided by the sample space. This is theoretical. So you roll a 6-sided die. Find the probability of each event. All right. I want to roll a 3. All right. The probability. How many times can you? How many ways can you roll 3 with a single die? 1 way. What's the sample size? 6. So the probability of A occurring is 1 in 6. All right. Now, the probability of rolling a 7. Have you ever owned a die that has 7 on it? No. So the probability of rolling a 7, P of 7, is 0. 0 divided by 6 is 0. You have a 0 probability of rolling a 7. Just won't happen. All right. The last one was rolling a number less than 5. Less than 5. So that's 1, 2, 3, or 4, right? So 1, 2, 3, or 4. There's 4 possible outcomes that will make rolling something less than a 5 true. So 4 over 6, which is 2/3, which is 0.667. So this is the classical or theoretical probability. Another type of probability is empirical or statistical probability. Looking at a sample, not a population, populations and samples, based on observations obtained from probability experiments, kind of like our text message experiment. Relative frequency of an event. So we count up using tally marks how many times an event happens based on total sample size. So the probability of an event E occurring is the frequency of E over the total N. All right, here's an example. A company is conducting a telephone survey of randomly selected individuals to get their overall impressions of the past decade, of the 2000s. So far, 1,504 people have been surveyed. That's our sample size. What is the probability that the next person surveyed has a positive overall impression of the 2000s? So we look at the outcomes of each: positive, negative, neither, don't know. The total positive, the frequency of the positive, is 406. The total sample size is 1,504. So the probability is 406 divided by 1,504. The event, divide it. So the probability, if we were to sample one more person, we would say the empirical probability would be of getting a positive thing would be 0.27 or 27% positive. The law of large numbers. The law of large numbers. As an experiment is repeated over and over and over, the empirical probability of an event approaches the theoretical. So the experimental one gets closer to the theoretical one, the actual probability. So if you were to toss a coin 4 times, you might end up with 3 heads and 1 tail. But if you were to toss this coin 1,000,000 times, the amount of heads and the amount of tails would become essentially the same. You'd come very close to 500,000 tails and 500,000 heads. Subjective probability. It's intuition, educated guess, and estimates. An example given is a doctor may feel a patient has a 90% chance of full recovery. That's based on feel or external experience. So let's classify them. We're going to classify the statement of an example of classical, which is theoretical, empirical, through an experiment, or subjective, kind of like feeling or experience. The probability you'll get the flu this year is 0.1. All right. Have they experimented with people and figured out what the probability is of one person getting the flu and not getting the flu? No. Have they actually ran an experiment yet? and counted how many people got the flu? No. So they are just projecting over past experience what's the chance of getting the flu. It's kind of a gut reaction. So this is a subjective. It's like educated guess. All right, here's another one. The probability that a voter chosen at random will be younger than 35 years old is 0.3. Okay. How do we know all the voters are going to be younger than 35? Is this a gut feeling? Or maybe they've looked at voting history. So it's empirical, based on a survey of looking at voting history. The probability of winning a 1,000-ticket raffle with one ticket. So if 1,000 tickets were chosen and you bought one of them, and your serial number on your ticket is unique, and every single is unique. So all 1,000 are unique. There's a 1 in 1,000 chance of winning. This is pure classical. Everyone in that 1,000 has an equal chance of winning. So let's look at the range of probabilities rule. All right, the range of probabilities, the probability of event E is 0 to 1 inclusive. It could be 0 or it could be 1, meaning you have an absolute chance of winning. So the probability is always between 0 and 1. Always between 0 and 1. So can I have the probability of winning the lottery at 115%? No, because the probability is always 0 to 1. So it's always going to be either 0, a decimal, or 1. So 0 is impossible, like rolling a 7, that's impossible. Or when I roll a dice, what's the probability of getting a 1, a 2, a 3, a 4, a 5, or a 6? Well, 6 chances possible outcomes over a sample of 6. 6 divided by 6 is 1. I am guaranteed that I'm going to get a 1 or 2 or 3 or 4 or 5 or 6. The complement of an event is E prime. It's the opposite. We know that the probability of an event is up to 1. So the complement would be 1 minus that probability. They add together. The probability of rolling a 1 or 2 is 2/3. The probability of the complement would be rolling 4, 5, 6, or 7. That's 4, 6, which is 2/3. 1/3 plus 2/3, it equals 1. So the complement of an event and the probability of the event added together will also equal 1. So now we could do a little arithmetic to show that you could subtract one of those probabilities from 1 to figure out the other. And sometimes that's easier to figure out what can't happen versus what will happen and just use the complementary of events theorem. So here's an example. You survey a sample of 1,000 employees at a company and record the age of each. Find the probability of randomly choosing an employee who is not between 25 and 35. Now, this list has 1, 2, 3, 4, 5, 6 categories. But what happens if the categories were 20 or 30 categories? So we know what the probability of picking someone 25 to 34 is. That's 366 divided by 1,000. To figure out the complement of that, we're just going to subtract 1 minus 366 over 1,000, which makes it much easier. So there's a probability of being between the age of 25 and 34. Now the complement is just 1 minus that, which makes the math much easier. especially when you have a lot of categories. All right. The probability experiment consists of tossing the coin and spinning the spinner shown. The spinner is equally likely to land on each number. Use a tree diagram to find the probability of tossing a tail and spinning an odd number. All right. So, with a coin, you have heads or tail. So that's 2 branches. Off of those 2 branches, you have 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possibilities, but you want an odd number. So you want a tail and odd. So it's 1, 3, 5, or 7. So there's 4 over 16, or you have a 25% chance of getting a tail and an odd number, because those are the only 4 positive events. And this is how you use a tree diagram. Now remember, when you go one more level, if you add another event that has multiple positive events, a tree diagram becomes very messy and hard to create. Probability using the fundamental counting principle. Your college identified number consists of 8 digits. Your student ID has 8 digits. Each digit is 0 through 9, which means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and each digit can be repeated. So you could have the number 0, 0, 0, 0, 0, 0, 0. So what's the probability of your college identification number when randomly generating 8 numbers? What's the probability of getting exactly the number how many different numbers are there? So each digit can be repeated. So in the first one, there's a chance of getting 0 through 9. There's 10. There's 10 choices for each digit. So it would be 10 times 10 times 10 times 10, 8 times. Right? So it's 10 to the 8th power. So there are 100 million different possibilities when using 0 through 9 8 times. That's a lot of different possibilities. Only one of these numbers corresponds to your ID, so the probability of your ID is 1 over 100 million, which is so small. All right, so let's go over the summary. You identified sample space of a probability experiment and identified simple events. You use the fundamental counting principle to find the number of ways 2 or more events can occur. You distinguish among classical probability, empirical probability, and the subjective probability. You determine the probability of the complements of an event, and you used a tree diagram and the fundamental counting principles to find probabilities.